Sure. Thank you. It's great to be back here. I did my postdoc here 10 years ago. To be back. And today I'll talk about strong bonds for arithmetic progressions. And this is based on joint work with Xander, who will give a more detailed talk tomorrow. I'll just sort of set the stage for him to actually do the work. And so the problem that we're going to talk about today is the 3AP problem, which was introduced by Erdős and Turan in 1936. And the question is the following. Suppose you have a subset A of integers from 1 through n. All we know about the set is that it has a certain number of elements. So we'll quantify that by saying its density is delta, meaning it has a delta fraction of the overall set universe. And how small can this delta be? Well, always guaranteeing that any such set will have 3 numbers which are equally spaced or a 3-term arithmetic progression. I'll just say 3AP for short from now on. Okay, and Behrend in 1946 showed that this delta cannot be too small. There exist sets whose density is roughly 2 to the minus square root log n that do not contain any 3 numbers in an arithmetic progression. Okay, so that's at least one limit that we know. You cannot have a really small density. Any such bound must be at least 2 to the minus square root log n. It's a beautiful geometric construction. If you're interested, I can tell you more about how it's also useful for a communication complexity problem that I'll mention at the very end, once again, in the context of open problems. Okay. And what do we know in terms of positive results? There's actually been a lot of work, starting with the seminal work of Roth from 1953, who essentially showed that delta roughly 1 over log n suffices. So as long as you have at least 1 over log n fraction of the total number of integers, you must contain 3 numbers in arithmetic progression. This was exponentially improved by Heath-Brown and Semerady to some small exponent of 1 over log n. And then Bourgain in 1999 and 08 improved it to 1 over square root log n and 1 over 2/3 of log n. Actually, Bourgain did not just improve the exponent, but introduced a number of techniques which have significant impact on all of the subsequent works, even including ours. I'll say a little bit about that later on. And there are many other works I'm skipping here, but I'm just mentioning the things that are kind of relevant for the results that I'm going to present in how we use them. And finally, 1 over log seemed like a barrier for showing any bounds. This was overcome by Bloom and Sisask in 2020, who showed that even if the density is some small constant, 1.01 or something like that, 1 over log n, even then you must contain 3 numbers in arithmetic progression. Besides the quantitative improvement, what's significant about this 1 over log n to the 1 plus something is that it gave first progress on another Erdős problem about divergent series of reciprocals always having 3 numbers in arithmetic progression, but that's a different story that I'm not going to touch upon today. And our result is that, in fact, the true answer must be close to Behrend's example, that there must be 3-term arithmetic progressions as long as you have 2 to the minus log n to the 0.09. Okay, so it says that maybe the truth is closer to the lower bound that we've always known. And it's not just that we showed there is a single 3-term arithmetic progression. In fact, many of the results that I mentioned before, even with 1 over log n and so on densities, they don't just show the existence of a single AP, they actually show the existence of many 3-term arithmetic progressions, almost what you would get for a random set. Okay. And that is also true for our work, but I'm not going to emphasize that much. All right, so in fact, I'm going to take a detour from the integer case and talk about this question in a slightly different setup. So the equation that we're looking for, or the set of, what we're looking for is a solution to the following equation. We want 3 numbers, A, B, C, from our set, which satisfy A plus B equals to C, right? And we can look for this not just over integers, but we can also ask this over any finite group. In this case, I'm just going to ask it over finite fields. So let's say I have now a subset A of fq to the n. The density is delta. How small can delta be such that I can find three distinct elements, A, B, C, from our set A, such that A plus B equals 2C. And over finite fields, the landscape changes dramatically. In fact, Behrend's example, the lower bound construction no longer works. So that's the first thing that goes out the window. The other, upper bounds still kind of work. But in fact, we know much stronger bounds over finite fields. In a breakthrough work due to Krutlepak and others, sorry, I forgot the names of the other of EG. And they show that even exponentially small sets must contain three elements ABC, which satisfy the equation A plus B equals 2C. Okay, so our finite fields, even exponentially small sets would have three elements. Over integers, we know that's not true. And for the case of Q equals 3, this is called the capset problem. And I recommend just focusing on that. In fact, I'm just going to focus on the Q equals 3 case because all of the ideas are kind of present, are required even for this case. Okay, as we'll see later. All right. And one notable thing about these works on capset is that they use algebraic techniques, more specifically the polynomial method, which says that number of such equations must correspond to some solutions to certain equations for finite fields, and they don't quite carry as easily to integers. Maybe, this is perhaps to be believed because we know that you cannot get such strong bounds over integers anyway. Whereas the previous techniques of Roth, Bourgain, Sanders, Bloom and Sisask, and so on, they use analytic methods, meaning they work with Fourier coefficients, Fourier analysis, and so on. And more or less, especially given Bourgain's work, it kind of set a template for doing stuff over finite fields and pushing it to integers. So all of these analytic proofs can be pushed to integers with extra work, extra non-trivial work. And in fact, one of the things that we do, the first thing that we do in our work is to give an analytic proof for finite fields with much worse density than what you knew from algebraic methods, roughly 2 to the minus log and the 0.11 again. But because it's using analytic methods, we can push these techniques to work over integers. Okay? And there's a significant amount of work required to do this, but I would say focusing on analytic proof for finite fields gives us a good picture of what's needed. And subsequent to our work, Bloom and Sisask gave a cleaner way to push the finite field arguments from our work to integers and also got some new improvements for other equations. Okay. All right. So for the rest of the talk, I'm going to focus just on the finite field case. And presumably Xander will have time tomorrow to talk a bit more about the integer case as well. Okay, so we have a subset A of subset A, density delta over FQ to the n, and we're looking for three unequal numbers that satisfy A plus B equals 2C. And we're going to give a proof that 2 to the minus log n to the 0.1 will suffice. And the proof has three parts. The first one is kind of the bread and butter in this area, which is structure versus randomness. And I should say that one nice thing about the 3AP problem is that, besides being interesting by itself, it actually has been very important in terms of giving rise to new techniques, which have wide applications. Like I think structure versus randomness goes back to Roth's original proof, which is really widely used within additive combinatorics and also in theoretical computer science and many other places. And the second part, which is newer to our work, is what we call spectral positivity. And I'll tell you what that means. It allows you to give lower bounds from upper bounds. And finally, there's this new idea of sifting, which allows us to find additive substructures within large sets using certain mechanisms. All right. So let me start with the first part. What is structure versus randomness? The structure versus randomness argument is basically a wishful win-win argument. It says, let's focus on the F3 case. You have a subset A of integers of F3 to the n. Density is delta. And the easiest case would be when the set A itself is a random set. So suppose A is a random set, completely chosen at random. The only constant is that the density is delta. How many 3APs would we expect? There are roughly n square such triples. Let me just count the number of solutions to the equation without forgetting ordering. There are n square such solutions, and each such solution should be present with probability delta cube. So if I choose the set A completely at random, I should expect delta cube n squared many solutions. And if this is much more than delta times n, many of them should be distinct. So that's a trivial way to get many non-trivial 3APs. So the first part of structure versus randomness is this wishful thinking that maybe we can come up with a notion of being close to uniform. I don't need the set A to be completely random, but maybe it satisfies some random-like or pseudo-random properties. We need to come up with this notion of close to uniform carefully, but maybe in that case, we can easily argue that it has many 3APs. That's the first part of the win. The second part is what happens if your set is far from uniform under whatever notion you chose. We would like to say that in this case, some structure arises. In particular, maybe if you look at that picture before, all of the points were kind of getting clustered on a single hyperplane. Right? So that's the structure that is very helpful for us, because suppose we can say that when you're far from uniform, you have more elements on some affine subspace than you should have. That your density when restricted to this subspace is higher. Then you have more elements here. So maybe we can do induction on the subspace. We are now going to work on V. Since we are over finite fields, all the subspaces, kind of are isomorphic, we end up with the same problem as before. Okay. And in fact, this is one of the reasons why studying things or integers is much harder, because there are no such nice substructures that you can do induction on. Whereas for FQ to the n, you can just say, okay, I have a subspace now. Subspaces are all the same, so we can just work with them from scratch. So wish 2 is if you're far from uniform, I want an affine subspace onto which I have more elements, relatively speaking, than before. Okay. And of course, I can't just say, okay, here's my single point. It's a subspace of dimension 1. I have density 1. Right? That's useless to me. We need a large subspace. And large subspace we'll often quantify by the codimension of V. So we need to be very, very large. So meaning its codimension, which is how many constraints you're placing, should be really small. Okay. So with this, let me do a quick review of Roth's argument as formulated in this elegant paper by Meshulam. I'll just call it Roth-Meshulam Proof to kind of set the stage for what we're going to do next. So the notion of close to uniform that works, that at least works, is being small bias. So what do you mean by small bias? Basically, suppose I pick a uniformly random element from a set A. It's a random element over FQ to the n if it fools linear test. Meaning, if I take some of my elements with some weights, the probability that equals 0 is 1/3 plus or minus some small error. Probability that equals to 1 is 1/3 plus or minus some small error. And probability that equals 2 is also 1/3 plus or minus some small error. And again, as I said, I'm focusing on F3 to the n just for concreteness. The same thing works for general FQ. So if it's close to uniform in the sense that linear tests cannot distinguish our set A from a uniform to random thing, then you should have many 3APs. Okay, this is the first step of Roth's argument. And then the other part of the argument, the win-win, the second part of the win, is actually almost tautologically true here. Because if I say that it's not small bias, that means there's a linear test which is distinguishing you from uniform. And that gives you an affine space immediately of codimension, in fact, 1. Right? So you place a constraint according to the linear test which distinguishes you from uniform, and that gives you density increment. You have a very large subspace codimension 1, but the density increment is tiny. And the density increment you get is you go from density delta that you started out with plus delta squared. Okay, so that's some improvement. So what happens if you chain this, right? So you started out with this set A, over F3 to the n, density delta. If I find 3 APs, I'm good, I'm done. If I don't find 3 APs, then I know that I can find a codimension 1 subspace onto which I have density increment, delta plus delta squared. I keep repeating this. And if I do it 1 over delta iterations, then I get a constant factor increase in the density that I started on. And you cannot do this forever. In fact, you can streamline it a little bit better to do say some additional factors, but that density can never be more than 1. So it has to stop at some point before you reach density 1. So this argument works as long as the starting density is 100 over n. And that's because you're basically running for 1 over delta iterations. So you will only get a contradiction when the starting dimension is bigger than that. Okay. So in summary, the theorem that you get is if I have a subset of F3 to the n, which has roughly 3 to the n by n elements, some big constant in front, then it has many 3 APs. Okay. So this is a basic argument that kind of the template that we are also going to follow with some twists. So the first twist is we're going to try and come up with a better notion of close to uniform, which maybe is presumably weaker than just fooling linear tests. And on the other side, we also want to say that when you're far from uniform, you want to get density increment. And for density increment, let's focus on how large a subspace can you find for which you have density increment by constant factor. Okay, instead of looking for delta plus delta square or other parameters, let's just set the benchmark as how small a subspace how large a subspace can I find while looking for a constant factor density increment. Okay, that's a kind of reference line for us. In the Roth-Meshulam argument, if you started out with density delta, you needed codimension 1 over delta because you had to do it 1 over delta. And to get the real improvement, you need poly log 1 over delta. So you need significant improvement in how large a subspace you're going to find for which you can find constant factor improvement. Okay. All right. So let's focus on this close to uniform. and we're going to almost take a minimalist approach, sort of look at the definitions and say what is sufficient and slightly change it. Excuse me. So we have one other way to formulate the question that we're looking for is the following. It's actually useful to think of it as set operations. So we're looking for triple ABC, A plus B equals to C. That's the same as looking for solutions to the following equation. So let A plus A denote the set formed by all pairs, all distinct pairs AB from a set A, and looking at A plus B. Okay, so just take any 2 elements, add them up as long as they're distinct, that is in A plus A. 2 times A is just 2 times the elements in A. Okay, so looking for solutions to A plus B equals to C where they're distinct is the same as saying I want A plus A intersect 2A to be non-empty. Okay. So if this is not empty, then I know that there is A plus B equals to C within my set. Okay. And non-empty is a pretty, it's weaker, but can we make it quantitative? Because often if you make it quantitative, maybe we can use other arguments to go along with it. And one suggestion might be to just look at the size of this intersection and say, maybe I want the size of this intersection to be somewhat big or something like that. But the right abstraction is to not just count the size, but also take into account that certain elements in A plus A might be representable in more ways than one. Right? There is some redundancy there because you're adding 2 things. Whenever they map to the same thing, they're just counted as 1 when you look at it as a set. But presumably, we should also take those statistics into account. Like how many ways can I express a single element as A plus B, where A, B are in my set. And it actually sounds cumbersome, but there's a simple probabilistic way to do this. And that's the following. I'm going to choose X and Y as independent and uniform over the set A. And I'm going to ask, what's the probability that x plus y lands within the set 2A? If this probability is close to what it would be for a random set, then I am good. If A was completely random, we know its density is delta. So x plus y should roughly, the probability that it lands within the set 2A should be delta. And I'm asking, okay, can it be delta or 100? Can it be delta or 1,000? Some constant factor in that. If this is true, then I get many 3APs. Most of the things work. Okay. So this is what we want from now on. And you might ask, okay, what's the distribution of x plus y? Well, this is like probability 101, right? If I have PDF of x, which I showed in blue here, the PDF of x plus y is actually much nicer. It's kind of smoother, it's flatter, and we have a formula for it. If the density of x is given by something, then the density of sum of two copies of it, two independent copies, is the convolution of the original density. Okay, so here by density, I don't mean the probability density function, but it is scaled so that the expectation of mu is 1 and not the sum of mu is 1. Okay, that's the right normalization that works through most of the calculations. So for every element in the set A, you have 1 over delta. Things not in the set A, it is 0. But you can just think of it as the probability density function of A. So if the density of A is mu A, then the density of x plus y is convolution of A with itself. And convolution, of course, has this formula. F star g is expectation over z of f of z times g of x minus z. So that is, you're taking f and g at two random points, constrained that the sum be x. And we're also going to look at something called the difference convolution, where you have a similar expression, but you evaluate f and g at 2 points where the difference is x. So there are two notions of convolution: the usual convolution, star convolution, and the difference convolution with the circle. Okay. So, this is what we wanted, going back to where we were. X comma we want, if I choose x and y independently and uniformly over A, we want their sum to lie within the set 2A with the right probability. Now I'm going to take a leap and not just ask this for the set 2A, but for every set with certain size constraint. Okay, so what is special about 2A here? Well, of course, it is special in the sense that the way we're generating x and y is kind of tied to 2A, but we also know that its size is big. So let me say, we have the heating property. If I choose x and y independently and uniformly over A, then for every set T, which is not too small, it has at least delta fraction of the elements, the probability that sum is in the set is big, is roughly what it should be. So instead of asking this just for the set 2A, I'm asking it for all not too small sets. It's kind of a substantial generalization, but you'll see that it doesn't hurt us. Okay, so let's parse this condition a little bit. So here I've written the entire universe f3 to the n on a single x-axis line. And y-axis is the density function. So for each point, it tells you what's the probability that you hit that as scale to have expectation 1. Okay. And 1 shown for reference here would be the uniform distribution. If the density of x plus y was actually completely uniform in f3 to the n, then you'd have the constant 1 function everywhere. So it need not be the constant 1, it can be ups, it can have ups and downs. We know it's not negative, that much we know for sure. So if I tell you, if I'm looking for this property, what would be the worst set T to choose? The worst set T would be those values, those points on the x-axis where the corresponding density is taking small values. Right, so I'm looking for the worst set T. The only thing is its size is at least delta n, and the probability that x plus y lands within T is small. So I'm going to take all the least probable elements and then put them into my set T. So in particular, if I look at all of these values, let's say which are at most 0.1, I mean, that's kind of like the constant there. Again, don't worry about the constant too much. So if you look at all the values on the x-axis where the density is at most 0.1, if those things in T have mass greater than delta, then we are in trouble. Right? If the blue region has delta and points, then we do not satisfy that condition, at least with constant point. Okay. So let me explicitly ask for this to not be true. So in other words, I'm going to say my density Q is anti-concentrated if the probability that it takes a value less than 0.1, which is the same 0.1 that we're shooting for, is at most delta over. Okay. So it's anti-concentrated in the sense that the probability it takes too small a value is small. And the too small is 0.1, and the probability being small is delta over T. And I'm just going to say anti-concentrated for this parameter from the one. We're not going to change the delta throughout. So the first notion of closeness that we're going to study is A is close to uniform in our sort of win-win analysis is it is close to uniform if A convolved with itself is anti-concentrated in the above sense. Okay, we want the density of A convolved with itself to be anti-concentrated. So far it's a little bit almost, by definition, you can argue that if it is anti-concentrated, then we have many 3APs. Just because, you'd apply it to the specific set 2A, the probability that it lands in 2A is at least delta over 20. And as a result, you get many 3APs. You get delta over 20 because there's at least delta over 2 points where your density is 0.1. So you just multiply them. Okay. So almost from the definition, we have one side of the win argument, which is if the density A convolved with itself is anti-concentrated, then we have many 3APs. Okay, to summarize the structure versus randomness part, we want to do this win-win analysis. If it's close to uniform, you have many 3APs. That's the first part. And the second part is if you are far from uniform, then you want to get density increment onto a large subspace. And we've seen the first part, which was relatively easy. We just said, if it is anti-concentrated, if A convolved with itself is anti-concentrated, then we have many 3APs. Next, we have to do kind of the harder part, which is to argue that if you don't satisfy this notion of closeness, meaning if you're not anti-concentrated, then you get density increment. Okay. And next, I'm going to argue. So the right thing would be to say that A convolved with itself is not anti-concentrated, then you get density increment. You can actually do a little bit trick to a little bit of arithmetic to show that it suffices to, I'm cheating a little bit, but ignore that, to even argue that if I take the difference convolution instead of the usual convolution, I want to say the difference convolution is not anti-concentrated, then you get density increment. Okay. Technically, you work with K norms and everything works out to be fine. But for the purpose of talk, let's stick to showing that if the difference convolution is not anti-concentrated, then you get a strong density. And you'll see in a little bit why this switch is happening and why it's important. But you can make this happen with norms if needed. Okay. All right. So that's the overview of structure versus randomness template and how we are going to use it. And let me now talk about spectral positivity and how it plays a role. So what do we want, right? We want to say that if A convolved with a difference convolution with itself is not anti-concentrated, meaning is far from uniform, then we get density increment. So let's understand this definition a little bit. So here I'm writing down the density of a difference convolution with itself. And it's not being anti-concentrated means that the set of values where it's taking less than 0.1 has some non-trivial mass. And usually when you think of being far from uniform or close to uniform, we think of point-wise errors, right? Like, maybe I measure the error with the uniform distribution, which is the reference value 1 here, and I count like maybe under some norm, you have some error, and you can use various things for that. If you think of it this way, then there are two kinds of errors or deviations from the uniform distribution. One are upward errors, where your density is taking too high values, or downward errors, where your density is taking values much lower than it should. And in our case, we just know that a difference convolution with itself has only downward errors. Meaning, we know that there is deviation downward. There are values where my density is taking something less than 0.1. So in particular, it's far from the reference one in the downward direction. Okay. And in general, this can be true that there are densities which only have downward errors. Okay. So I can have a distribution which looks like this. Basically, it's very close to 1 in the upward direction, but it has large deviations in the downward direction. Okay. And one of the things that we exploit is that this cannot actually happen for a large class of densities with a special property. In particular, we showed that if your density is spectrally positive, then you cannot have just downward errors. So what do you mean by spectrally positive? Spectrally positive just means that all of the Fourier coefficients of your function are non-negative. So you have a density, it's on F3 to the n or any space, do Fourier analysis, look at its Fourier coefficients. If all of the coefficients are non-negative, then it is spectrally positive. And if it is spectrally positive, we show that you cannot just have downward errors. If you have downward errors, you must also have upward errors. Quantitatively, what this translates to is if you are spectrally positive and not anti-concentrated, which was our way of saying you have downward errors effectively, then you must be taking large values too. In particular, the K norm for K, which is roughly log 1 over delta, is at least 1.001. Okay, so you are going to take larger values too, as quantified by this K norm for K, which is log 1 over delta. Okay. And the K norm again is with respect to expectations. You're just looking at the expected kth power of the density. So why is this useful for us? Well, spectral positivity turns out to be satisfied for us for free. In particular, for any density P, self-convolution gives you something which is spectrally positive. Because always convolution is much nicer in the Fourier world. If I take the usual convolution, then the Fourier coefficients get multiplied. If I take the difference convolution, they get conjugated. So you basically get, if I do self-difference convolution, then the new Fourier coefficients are squares of the absolute values of the old Fourier coefficient. So in particular, they're all positive. Okay. So if I combine these two things, spectral positivity, which is a statement about general densities, which are spectrally positive, and the fact that difference convolution is spectrally positive, you get the following. If a difference convolution with itself is not anti-concentrated, then the K norm of this difference convolution with itself is somewhat big. Again, K is roughly log 1 over delta. Yeah.
Where does delta appear in the statement?
Right. So delta is in the anti-concentration definition. So it should have been maybe not delta anti-concentrated, meaning the probability that it is less than 0.1 is greater than delta over 2. Okay. Yes. Sorry. That's a good catch. Basically, the delta is in the definition of anti-concentration. Any other questions? Okay, so in summary, the spectral positivity part would say that if A self-convolution is not anti-concentrated, then you get this, get the fact that you should be taking large values too, as quantified by this K norm. And you might wonder, why is this sort of switch from talking about downward errors, which was anti-concentration, to upward errors is so useful? Intuitively, it could be useful because what is our goal, right? We want to look for density increment. So we want to say something about the density, taking high values on some structured set, right? So at least, just in terms of, we're talking apples to apples now, because we have that your density is taking high values at certain collections of points as quantified by the K norm. But we want to now say that it's not just true that it's taking high values, it's actually taking high values on some structured set, particular a subspace with small codimension. Okay, so that's one intuitive reason why this switch is helpful. And if you actually do the math, it is actually very critical. Okay, so the next step would be to say that if a difference convolution with itself has high k norm, let's say 1 plus epsilon, think of epsilon as some small constant like 0.01, then we're going to show that you get density increment onto a large affine space. Okay. All right. So let me now go to the third portion, which is sifting, which is where we really find these structured subset onto which you have density increment. Okay. So again, our goal is just starting with a difference convolution with itself, k norm being large, and we want a density increment. And so density increment just means we want a large affine space where A intersect V is, at least 1.01, some constant factor better than what it was before with the original space, right? So jumping to a full subspace seems like a big step. I'm asking for a subspace onto which you have a density increment. A subspace, of course, is a very, very constrained set. It has to have all kinds of properties. In particular, if I look at V plus V, you're going to get back the subspace V itself. Right? It's closed under addition. You can add how many ever copies you want. You're just going to get the same set. Right? So as a way towards this, finding a large affine space onto which we have a density increment, let me ask for something a little bit weaker than finding a subspace. Can we find density increment onto a set with some additive structure? Maybe it's not a full subspace, but it has some additive structure. In particular, can we find density increment onto a sumset? Sumset means I take two large sets B and C, and I look at all things that I would obtain by adding pairs of them. So B plus C. Okay. So if I take a subspace and add it to itself, of course, I get the same thing. So if I can do this, obviously I can do this, but this might be significantly easier. Okay, so looking for a sumset could be significantly easier. All I'm asking is that it be representable as something of the plus C. Okay, and of course, again, when we're talking about sets, you have to take the counts into account. That's the right way to do the normalization and everything. But let me not, I'll mention that a little bit later, but let's just think of it as set addition for now. Okay. And let me do a caricature of how we do it. Again, this is very non-representative because I don't know how to throw F3 to the N. But so let's say we have some large set within F3 to the N. Okay. And we believe there is some additive structure hidden within it. Like, we want to find a large affine space. We want to find some sumset onto which you have density increment or something like that. So pictorially, I'm showing that additive structure as this grid. Okay. And we want some operation or something which will sift out the part which has the additive structure and throws out the remaining. And we want to identify some subset onto which you have density increment. Okay, that's the additive structure, which is being caricatured as this grid here. Okay, so the idea that we use, and is also used in some other works before, but in a different context, is to look at shifts of your set and intersected with this set. Okay, so the intuition is that you're looking for something like a subspace hidden inside, right? A subspace, if I shift it with something within the subspace, you stay the same. So when I do this operation of shifting by random element and intersecting, and then shifting by random element and intersecting, presumably, like for instance, when all of the shifts are within the subspace is going to survive. the intuition is the additive structure part is more is more likely to survive than the non-structured part. In this picture, for instance, if we take a shift along S1, you move somewhere else. If I take a shift along S2, you move somewhere else. But you can see that the grid portion is likely to survive when you take the intersection. Okay, the same thing or at least we're hoping would happen even when you have when you do this for subspaces. Okay, so that's the intuition that somehow when it takes shifts and intersect with itself, the fraction of the inner square in this picture is more likely to survive than isolated points. And in our real context, we expect the portion which has additive structure is more likely to survive than the one without. Okay, and the main lemma then is the following, which I'm not going to talk about how we prove it. Xander will talk about it tomorrow. But basically, the statement is something like this. So we are going to apply the sifting operation to the set of values where the density is big, right? So recall our assumption was good for us now. We know that we have a large set of values where the density is high. The K norm was big, so you can translate it to say that there's a set of points where a difference convolution with itself has large values. But this is just an arbitrary set at this point. We don't have any additive structure within it. What we'd like to say is that there is actually a portion within this set where you're taking large values and you have additive structure. Like if S itself was a subspace, then we're very good because you immediately get density increment. What we're trying to say is that S is not quite a subspace, but I can at least have some set structure within it. In particular, there are two large sets, B and C, such that their sum is almost like S. Okay. Again, as I said, to quantify it, you have to take into account how many ways you can represent things. So the right formulation is there are two large sets, B and C, where if I take X sample uniformly from B and Y sample uniformly from C, the probability that their sum lands within this set S is very high, like 0.99 or something. And this translates to saying that you can find density increment of S onto a Sumset. Right? And the proof of this lemma relies on some kind of a first moment method style argument. It's not exactly that. You have to set it up right. And in particular, there's a generalization of an identity like this, which plays a key role. So basically, if you look at this shift and intersect operation, especially for random shifts, there's a clean formula which tells you how big a set you end up with. Okay, and how big you end up with actually depends on the K norm of A's difference convolution with itself. Okay, you can get a more general form of this and then use it along with some kind of P-general principal argument to get the sifting level. Okay, that's all I want to say about the proof of the sifting lemma. But basically now we have this density increment onto a Sumset, but we're not there yet. We want to go to a subspace in the end. But fortunately for us, this step has been done before. In fact, we just use, it's also known as almost periodicity in some other works. The specific lemma we use is due to Sanders, which says that if you have density increment onto a Sumset, in fact, you should also get density increment onto an affine space. There is some loss in parameters, but you essentially can say that if there exists B comma C of density 2 to the minus L, meaning you're missing 2 to the minus L fraction, then you should also get density increment onto an affine space V, where the codimension is L to the 4. Okay, so it's a polynomial loss in the codimension compared to the density, but you get a subspace instead of a Sumset. Okay, so if we combine these two things, the sifting lemma along with the Sanders's result, you get that if your K norm is big, is at least 1.01, then you get density increment onto an affine space, a constant factor increment of codimension K to the 4 log to the 1 over delta. And delta here is again the density that you started out with. All right. And to give the entire proof summary now, you started out with this, we started out from here. If A difference convolution with A is anti-concentrated, then we get many 3 APs. Okay, so there's a small star here that you don't actually work with anti-concentration, you work with K norm, but let's ignore that. And then the flip side is if A's difference convolution with itself is not anti-concentrated, then spectral positivity tells us that you actually get many points where you're taking high values. You have upward errors. In particular, the K norm of the difference convolution is at least 1.01, where K is the delta in the definition. And then to finish it off, you have the sifting part, sifting plus the almost periodicity part, which tells you that whenever you have K norm, which is big, you must get, there is an affine space onto which you have density increment, and the codimension is polylogarithmic in the density, 1 over delta. Okay. So K is like log 1 over delta, so you get K like log 1 over delta to the 8. You need to do 1 more log 1 over delta, so you get like to the power 9. Okay, so if you put all of these things together, you get the statement over finite fields that whenever I have a subset of FQ to the n, which has density, which has roughly delta fraction of the elements, there are 3 unequal elements which satisfy A plus B equals to C. And the proof basically requires density, which is 2 to the minus log n to the power 1 over 9. And the 9 comes from what I just said. So for instance, if you improved Sanders' almost periodicity from like L, it had a loss of like, L to L to the 4. If it was actually tight, you might get something like log n to the 1/3 here. Okay. And going from finite fields, the argument that I presented to integers is quite technical, but it also has all of the ingredients. Like you still do sifting, you still do spectral positivity, and so on. Our original proof was actually a bit more complicated, but Bloom and Sisask, as I said, kind of simplified it by using like Bohr sets more directly. And this is what gives us the main theorem. There's some more loss when you go to integers as opposed to just finite fields in the exponent, but it's about the same. Okay. So that's all I want to say about the proof, and hopefully I'll say more details tomorrow. And let me finish with some natural next steps that we could shoot for. One obvious question that that might come up is, what about 4-term arithmetic progressions, right? So I mean, going from 3 to 4 is usually pretty hard. Like you can't just take Roth's argument and say, okay, I'll go to 4 and maybe get some weaker parameters. That's not quite true. We have to do a lot of other stuff. So it's not clear, but we are hopeful. And there's another question which kind of comes from this communication complexity thing that I briefly mentioned, which is the following. Now I'm looking for subsets of pairs of integers, not just subset of integers 1 through n. I have 1 through n squared. And the only thing again that I know is that it has delta fraction of the total number of pairs, which is n squared now. How small can this density be? While always guaranteeing that you get a corner. Corner just means a triple of points A, B, C such that the length of A minus C is equal to length of B minus C, and they're basically along the X and Y axis. So I want to find 3 points X, A, B, C, such that one is X comma Y, X plus D comma Y, and X comma Y plus D. And this has connection to a very beautiful question in communication complexity. And the best example again is from AP free sets. So Behrend's construction actually says that there exists a corner free set which has density 2 to the minus square root log n, and the quantitative bounds for corner free sets are much, much worse. Like the lower bounds are weaker than what we know. And it's a harder problem than 3AP, so maybe there's some progress that we can do here with new techniques. Okay, so let me finish with that, and if there are more questions, I'll take them. Questions? Yeah.
Yeah, so maybe one case which could be in between the corners and the AP4 could be also the square. The square, if you want to have a square, it could be simpler than AP4.
It's harder. It's the other way around.
No?
No quantitative bounds, no spreads at all. Yeah. So so you mentioned that if you can replace Saunders like K to the 4 with a black box that got optimal results, you could replace a ninth with a third
For finite fields.
so finite fields. Yeah. If you the sifting also seems inefficient. I mean, like, what's the natural limit of this? Could you get a sifting? Could you get a half, or could you get one? Or I mean, one seems a lot to hope for. But,
Maybe you could do even half. So 1/3 is coming up because of two reasons, right? So if you do it right, you would have K to the log 1 over delta here. So that means that somehow you're getting log squared 1 over delta. So which is, I think, so you're getting constant factor increment with codimension log squared 1 over delta. And then you have to do it log 1 over delta times to go from constant to to get a contradiction. But sometimes you don't have to do it exactly like this. Like in Roth's argument also, there's a way to sidestep this sort of final log 1 over delta where you don't have to say, okay, constant factor, I need 100 over n, and then I keep repeating it. So I think if you maybe, if you replace this L with L here, I don't know if it's actually how plausible that is. But if you do, I would, I think you might be pretty close to getting the right answer.
so the right answer is a half or one.
I think half.
Okay.
Yeah.
Yeah, so is there, it seems that the parameters don't align, but is there any hope for a reduction from the finite field to the general case?
Of integers?
I mean, the best construction we have almost looks, for the lower bound still looks like embedding it into log n dimensions, right? Like it's a log n dimensional sphere.
Okay.
Right?
You mean Behrend's example?
Yeah.
Yeah, that is true.
So,
yeah, that's actually a good question. I think, if when you think of it in terms of these sets, it seems harder, but maybe.
so Q to the log n is like a torus instead, and it's harder to make a torus or AP3 than. So the fact that there is an AP in every torus, when you embed it into a torus, doesn't mean that you get an AP downstairs, but it might be completely hopeless just because the parameters seem to be kind of, you'd have to be very precise,
Right.
to go from polynomial to
Right. Okay. So
polylog.
I don't know about this set construction, but in terms of protocols, there may be a reduction. The parameters seem very different here. Like it's 2 to the root log n versus something else. But if you talk in terms of log, you can say, what if I have a protocol over finite fields? Can I get a protocol over integers, which is quadratically worse? That would give you something like this. So
Also simultaneously, if I was allowed to use many queues, of course, this wouldn't work with anything else, but
right.
in communication world, it makes sense.
Exactly. Like, you can think of it, if you think of it as a simulation question, then, it's only quadratic loss in the number of bits. It's plausible, but at least we don't know any such thing. Any other questions?
Okay.